Okay, last time we pretty much wrapped up chapter 16, except for one topic, which we're going to officially talk about here today to finish up. But we were talking about acids and bases, and we're talking a lot that time about a lot of different things, including how to calculate pH, pOH, and whether or not a solution is acidic, basic, or neutral. A reminder that, again, the pH scale, which is typically the one everybody sort of thinks about, goes from 0 to 7 to 14. Again, less than 7 going to be our acidic region, above 7 going to be our basic, and our 7 there going to be our neutral. Again, as we go towards 0, we become more acidic. As we head towards 14 there, we're going to become more basic in that case. We saw a number of sort of formulas to calculate a variety of things, including Kw, which is our concentration of H plus times OH minus, equals that 1 times 10 to the minus 14, which again is a constant number that you always have available to you to really calculate both of those things, either the H plus or the OH minus concentration. We also had our pH is equal to minus the log of our H plus. Remember, there's a similar scale where we could calculate our pOH using the OH minus concentration. Once again, both of these things really tell you what you need to calculate those. We also talked about using our calculator here. Again, if you have a display calculator, pretty much you're going to punch it in exactly the way the formula is. If you have a non-display calculator on all these, you pretty much have to work your way backwards, usually starting with a number and kind of punching it in that way. The relationship between these two and why it's useful sometimes to calculate, say, the pOH is if you take the pH plus the pOH, again, that's going to be 14. So that does give you a variety of ways you can kind of solve some of these problems as we did last time. If you have just the hydroxide concentration and you want the pH, I could actually calculate the pOH first and then just subtract 14 and then you'll have the pH. So that's one way you could do it. You could also, as we talked about, still use Kw. So you could take the OH minus concentration and get the H plus concentration from Kw and then go into the pH equation as well. So they all really should give you the same answer depending on which way that you go. We also saw that if you do have the pH, from that you can get directly the H plus concentration, which is the inverse log of the minus pH. And once again, on your calculator, that usually will pop up like a 10 and a caret when you do the inverse log. That's usually like the shift button or second button and the log button on most people's calculators. And again, you want to make sure that you do make it negative when you go in there. Again, don't use the subtract button either, obviously. pOH, you can get the OH minus concentration. Pretty much the same calculation. But the good news on a lot of these is it's pretty much the same calculations, regardless if you're starting with the H plus or OH minus concentration. And you can have each of those. We finished up talking about that. Sometimes you may not just be given a generic sort of concentration of H plus or OH minus, or a reminder again that H3O plus and H plus are basically the same thing. But you may be given a formula of a strong acid or a strong base. So if you have a strong acid, it will 100% break apart. And really what you want to figure out from that would be what is the H plus concentration in that solution. Since as we put that list up last time as well, there's only like 6 or so kind of really strong acids, and most of them are monoprotic, which means they give away 1 H plus. Pretty much if you know the concentration of the acid, you will know the concentration of the H plus in that solution. So you could really go right into the pH equation. Strong bases, same thing almost, except that they will obviously 100% break apart as well. But here, because they are bases, what that's going to allow you to do is to get to the OH minus concentration. And from the OH minus concentration, you get the pOH, you can subtract 14 and get to the pH. So a little bit more work there with the strong base. Remember that most strong bases are found on the periodic table there in group 1 and group 2 that have hydroxide in the actual formula. So again, starting somewhere up there like sodium, lithium, and coming down to potassium, hanging a right by calcium and coming down. Any of those guys that have hydroxide in the formula typically will be strong bases. Out of the two, as we talked about last time as well at the end, probably the strong bases is probably the one that you might have to worry about sort of adjusting the concentration of the hydroxide. I think we did calcium hydroxide there in that last example. Remember that you get 2 hydroxides, which means you just to kind of adjust the concentration by 2, so you get the right hydroxide concentration. Again, with the strong acids, probably going to be a monoprotic acid, so it will probably be the same H plus. Any questions on any of that stuff there that we talked about there in this chapter? Okay, so this finished the last topic, which we talked a little bit about in lab last time, but we'll officially talk about it here. And that is buffers. And a buffer solution is a solution that will resist changes in the pH, even when you add more strong acid or strong base to it. So we did that lab the other day, and most of you had like hundreds or so of drops needed to change the pH of your buffer solution. And that's because it is able to resist changes if it is made correctly. As I mentioned last time, a really misunderstanding that sometimes people again have with a solution that is a buffer is that they always assume that it's neutral. And that's not always the case. Once again, you can make a buffer at any pH you like. It just means wherever it starts, it will be able to maintain its pH even when you add more acid or base for a good period of time. So a buffer does not necessarily mean that it's a neutral solution, but it is a solution that can resist changes in pH based on wherever it actually starts. And the real reason why it's able to do that, as we'll talk about here in a second, is really what it is made out of. So a buffer is really made out of one of 2 combinations. You can have a weak acid and its conjugate base, or sometimes referred to as the salt of its conjugate base. You could also have a buffer that is made out of a weak base and the salt of his conjugate acid. So those 2 things have to be in the buffer solution to begin with in order for it to actually operate correctly. They're actually both in there to start with. One thing that you cannot have a buffer cannot be made out of a strong acid or a strong base. So there is no way for a buffer to be made out of those 2 things, a strong acid or a strong base. It has to be a weak acid or a weak base in order to allow the buffer really to function correctly. So why is that? Well, it is because you essentially need to have in that solution, if it is a buffer, an acid part and a base part. So if it is to be a buffer, you got to have both an acid part to that buffer and a base part to that buffer. So for example, if we took something like HF and NaF, and these are a weak acid and its conjugate base. Now, what is a weak acid and its conjugate base? It's the same definition as we talked about with Bronsted-Lowry. The only difference between them is an H plus difference between those 2 things. And if we look at really this guy here, which is our sodium fluoride, that is going to be a sodium ion and a fluoride ion. And it actually is the fluoride ion that is the actual part of it that's doing the buffer work. It is the conjugate base to HF. The only difference between HF and F minus is that H plus, right, which is the Bronsted-Lowry definition. The sodium there is just hanging out. It's really just a spectator ion. It's there to balance out the charge. And that's why it's sometimes referred to as the salt of this conjugate base, because it has a salt that's just an ionic compound. So that's what the sodium is there for, not really doing anything in terms of the actual buffer part of it. So why does this work well? Well, because this is a weak acid, this is a weak electrolyte, which means when it is in solution, it's going to break apart a little bit into these two things. And it's going to set up this equilibrium, which is essentially in this beaker going to keep HF and F minus present in the actual beaker to start with. And that's really important because, as we know, it's a weak electrolyte, which means it's mainly going to stay together, but will produce a little bit of those ions there. And because it's able to basically set up this equilibrium, we now have our acid part of the buffer, and we now have our base part of the actual buffer, and they're both being able to basically stay in solution. We actually help this out a little bit by adding a little bit more sodium fluoride to the mix, which will increase the amount of fluoride F minus in that solution. So it'll kind of keep it in the solution there in pretty good amounts. And this is why, for example, a buffer needs to be either a weak acid or a weak base, because they'll be able to set up this equilibrium and they'll be able to keep both parts in solution at the same time. You'll be able to have that acid part and the base part of the actual buffer itself. And that doesn't happen, for example, if we were trying to make a buffer out of hydrochloric acid and say some sodium chloride here, which would technically be Cl minus as its sort of conjugate. When I would go to do this and put it into here, the problem is this guy right here is hydrochloric acid, which is a strong electrolyte, which means it is going to, when it goes for a swim, not stay together. It is going to 100% break apart into these guys, which means if I look at my buffer now, what I have in that solution is H plus, a lot of H plus, Cl minus from the acid. I also have some sodium ions and chloride ions there from my base. And in this case, the only thing that we have in the solution is the base part of the buffer. We do not have the acid part of the buffer. So because a strong acid or strong base will not stay together, it will not be able to have in that solution an acid part of the buffer in the case of an acid, or the base part of a buffer in case of the base. You will get the conjugate partner, but that's not going to do you much good because you don't have the other part of it. So that's why a buffer itself has to be made out of a weak acid or a weak base. They're the only weak electrolytes that will actually set up that equilibrium, be able to keep both the acid part of the buffer and the base part of the buffer actually in the solution at the same time. Any questions on that there? Yeah. So what we're talking about here, acid part and base part, we're actually talking about the buffer itself. We're not talking about adding any additional acid or base to it, but this is how basically a buffer is able to stay in there. So for example, in the experiment that we did the other day, you threw in some acetic acid, which is a weak acid, and you threw in some sodium acetate, which is a conjugate base to it. And again, because acetic acid is a weak acid, it will set up an equilibrium that keeps the acetic acid in the solution and the acetate in the solution, which again would be your acid part of your buffer and your base part of the buffer that you made in that particular example. So why is it really super important that we have both of those things in the solution at the same time? Well, if we were making a buffer, we probably want to keep the pH fairly maintained at wherever it starts. So for example, if we did this, if we took a strong acid now, like hydrochloric acid or sodium hydroxide, and we added it to a non-buffer, like I think you guys had deionized water maybe in your other beaker or something like that, maybe. So if we add to water, which is a non-buffer solution, and if we added some hydrochloric acid, which is a strong acid, to water, what's going to happen is essentially it is going to 100% break apart into H plus and Cl minus in this case. So if we add to water that's HCl, we will get 100% these guys, which means if we look at our beaker and we added this HCl into this water, we would have now generated a bunch of H pluses and a bunch of Cl minuses, basically, right, in this particular case. And this is not really good because if we think about the pH formula, the pH is equal to minus the log of the H plus. What I just did by dumping that hydrochloric acid into the water is I definitely here by my picture see an incredible increase in the amount of H plus very quickly, right? So you just basically littered that water with a much more H plus than was there before, or H3O plus. And when the H plus concentration goes up, the pH is going to drop a lot here. So for example, if our water started at a pH, say, we'll say 7, for example, and you added some hydrochloric acid to it, by increasing the H plus concentration in that water, by adding the acid, perhaps the pH goes from 7 down to like a pH of 2, a really big jump in pH, because you pretty much just introduced a ton more of H plus that wasn't there to begin with. And that is what we would expect to happen when you would add an acid to a non-buffer situation. You would increase the H plus concentrations, which would result in a pretty big swing in terms of the pH of that solution. I think similar to the other beaker that you had in that experiment where maybe you just dropped 1 drop and the pH changed by like a pH of 1 or something like that, right? And that's clearly not a buffer, right? So that little amount added a lot of H plus, was able to change the pH really quickly. Now, if we look at adding a strong base to water, so if we added again to water, which is not a buffer, a strong base like sodium hydroxide, when we would add sodium hydroxide to water, it also, because it's a strong electrolyte, will 100% break apart into sodium ions and hydroxide ions here. So when we look at it here, and we took our sodium hydroxide and we dumped it in there, we're going to produce a bunch of sodium ions. But more important here, we're going to produce a bunch of free OH minus ions in solution. And if you remember, the concentration of OH minus and the concentration of H plus are linked to each other, which means what we're going to see is an incredible increase in the amount of H plus, which means by default, the amount of H plus there will go down. The result of that is we will see the pH jump higher because there's now a lot more OH minus in that solution than there was before we began, making it more basic, right? Kind of like this KW, more OH minus than H plus in this case. And we're going to see a really big jump in pH again. So here, if your water started at 7, you maybe add some sodium hydroxide to it, maybe it jumps to a pH of 10 or 12 or 11 or something like that. So a fairly sizable jump in pH, again, because we just introduced this solution, much like in the acid case, a bunch of OH minus really quickly. Now the solution has a lot more free OH minus floating around than it did before it began. Any questions on what happens in a non-buffer situation here? So let's see what happens if we take the same strong acid and we take this same strong base and actually add it to a buffer. So we'll use the one I just did, which is different than everybody's favorite example of acetic acid and sodium acetate. But we'll use hydrofluoric acid and sodium fluoride. So this is going to be our buffer in this example. This again is our weak acid. This is our conjugate base. Again, the salt of this conjugate base. And once again, a reminder that it really is the F minus part that is really the buffer part of that. The sodium, again, it's just hanging out there to balance out the charge. It's a neutral ion, so it's not going to do much. So again, in this case, you could think of the HF as the acid part of the buffer. And you can think of the sodium fluoride here as the base part, basically, of the buffer. So once again, if we had a beaker of this guy here, we would have this equilibrium basically set up. It probably wouldn't have the arrows, but we'll just pretend here. And we'll do a little bit of this, basically. So once again, that is our base part. That is our acid part. And we again would help ourselves out here by probably adding a little bit more, again, sodium fluoride to it, just to make sure we have a pretty good concentration of each of those ions in solution to begin with. So now we're going to take the same acid that we did on the previous example there. We're going to take some HCl and we're going to add it to this buffer. So I'm going to take some HCl. This is obviously our buffer down here. And we're going to add it. When I add HCl to the buffer, HCl, which is a strong acid, will actually react with the buffer that's in there. And which part of the buffer should the HCl react with? The acid part or the base part? They're called acid. What type of reactions? Acid base reactions. So when you add the HCl to it, it's actually going to go and react with the base part of the buffer. So when we add that HCl in, the HCl is really a source of these two things, H plus and Cl minus. So we have our H plus coming in and our Cl minus. It is going to react with the base part of the buffer, which is really the F minus. So we're going to get a reaction here of really our base part. And this is going to be a double displacement reaction. That's a positive, negative, which means these guys are going to basically just switch partners. And what we will form on the other side is HF and a little sodium chloride. Any question on that reaction? So we're going to dump this acid in. The base part of the buffer is going to really go into effect here and start reacting with it. And what we see here that is formed as a result of this reaction is we actually formed HF, which was part of the buffer to begin with. And by the way, that always happens when you add an acid to a buffer. You make more of the acid that was originally there for the buffer part. As we'll see in a second, we actually will see the same thing happening when we add the base. We also have sodium chloride, which is a neutral salt. And it's a neutral salt because of the relationship that we talked about also in this chapter, which is sodium chloride basically comes from a strong acid and a strong base is pretty much where it would come from, which means it's going to be relatively weak and neutral and not really react. So we just made in the result of this more of the buffer, and we made a neutral salt, which is a sodium chloride. And it's actually what we do not see here. That is why the pH doesn't move around so much. So what do we not see here that we did see when we added the acid here to water? When we added the acid to water, we made what on this side? Made a bunch of free H plus really, really quickly. Now, when we added that same acid to the buffer, there is no H plus made. And that's because this H plus and this F minus are going to come together and make some more of the HF. So that's not going to be free in that solution. It's going to get tied up with the F minus and actually make the HF in this particular case. So because in this case, no H plus was made, no more H plus, free H plus was made. That means that essentially the amount of H plus that was there to start with is still the amount of H plus is there now. So essentially the concentration of H plus stays relatively constant. And because of that, the pH will stay relatively constant as well. So because when we introduce this strong acid to the buffer, the base part of the buffer is able to pretty much tie up any free H plus that would form with it not being there. We keep pretty much our H plus concentration relatively stable, and that keeps our pH relatively stable. Will it actually move if you were monitoring it? The answer is yes, it will move a little bit. So maybe our pH started at, we'll go with 5.6 or something like that. And we add some acid, maybe it drops to 5.5 or something like that, but not a giant jump in pH. So you won't see this incredibly giant jump in pH because at most you're adding just a very, very small amount of H plus to change the pH a little bit. And you're doing that because essentially what's going to happen in this case, I'm going to make more HF, which will break apart a little bit more and produce a little bit more H plus in that solution, but not a tremendous amount of H plus like you have when you add the HCl to water, which all it has to do is go for a swim and you got H plus all over the place. Here you're going to have pretty much the same amount that you started with, just a little bit more maybe, which will make the pH go down just a little bit more, but not a tremendous jump in pH. Question on that there. And that is, by the way, when you make a buffer, how you can actually adjust your buffer to the right pH. You could actually dial it in by, adding some acid or base to it, and you could really dial it in. As you kind of saw with your drops there, you have to add a lot of drops to get a very significant change in pH of 1, right? You had to do a ton of drops. So if you just missed your pH when you made it, your buffer, and it's just a little bit off, you get a little bit of acid, and you can kind of really dial it into exactly sort of the pH that you want, to the exact number almost, pretty much. Any questions on that there? So let's then take a look at what happens when we add a base to a buffer. So let's just say we had our same buffer here, our HF and our sodium fluoride. And again, in this case, we're going to have our beaker where our weak acid is going to set up that equilibrium. And again, here we have both parts of our buffer, our base part and our acid part. So now what we want to do is we want to add some sodium hydroxide here to our buffer. So we're going to add some sodium hydroxide here to our buffer, which once again is a source of sodium ions and hydroxide ions that are going to go for a swim when you drop it in there. Since sodium hydroxide is a strong base, it is going to react with the acid part of the buffer in this case, right? So that makes sense. So when this guy comes in, it is actually going to react with the acid part of the buffer. And when it does so, we once again will get a reaction, which is a double displacement reaction, or really just an acid-base reaction here, where our guys are going to switch partners, and we will make NaF and a little bit of water. So we're going to make a little sodium fluoride and a little bit of water in this case. Once again, as you can see here, we actually made the other part of the buffer. So we made this guy, which is again part of the original buffer, which again always happens. We made water, which is neutral in this particular reaction that occurs. Once again, it is actually what we do not see here in this reaction, which is really important as to why the pH doesn't change. And again, if we take a look back at to what we did here, when we added this base to water, we produced a bunch of OH minus really, really quickly. And that's because in water, it's just going to fall apart and produce that OH minus. In this case, when we added this base to our buffer, this OH minus is going to come together here and make water. And that OH minus is not going to be allowed to basically be free in that solution with the buffer. It's actually going to get tied up into water, which means the OH minus will not be free. And thus what happens in this case is it is no free OH minus present. are made. It's a better way to make it, are made. And what that means is the concentration of OH minus stays relatively constant. And if the concentration of OH minus stays relatively constant, because OH minus and H plus are tied to each other, that means that the concentration of H plus should also remain relatively constant because they are related to each other. And if those both pretty much stay constant, the pH will also remain relatively constant. So once again, in this case, the amount of H plus that we originally had in the solution is going to be pretty much the same amount that you have after you add the sodium hydroxide here. Once again, if you were monitoring the pH with like a pH meter or something like this, you would see the pH go up a little bit. So it won't stay exactly the same. It'll go up a little bit. So again, it's 5.6, maybe it goes up to 5.7, something like that. But again, it will not go from like 5.6 all the way up to like a pH of 10, a giant jump in pH or anything like that. A very small, modest change that would happen. And that's again because we're essentially keeping the amount of H plus that was in that solution pretty much constant throughout the both parts. So this is really why it's extremely important that if you want to make a buffer, you should always make it out of a weak acid and its conjugate base, or a weak base and its conjugate acid, because if you do not do that, you will not have the acid part or the base part that needs to be in that solution to maintain the pH. And we're able to basically maintain the pH by essentially preventing one of two things from happening. When you add an acid to your buffer, it prevents the formation of free by itself H plus, H3O plus being in that solution floating around. When you add base to a buffer, it prevents the formation of free OH minus basically floating around that solution. And by preventing the formation of more H plus or OH minus, that allows the H plus concentration basically to stay relatively constant. And that's what keeps your pH from going crazy and jumping all over the place. It allows to keep the pH relatively constant. Question on that there. Now, by the way, let's just say you wanted to be a rebel and make a buffer out of HCl and say sodium chloride, which is a bad idea. Once again, as we talked about before, what you're going to have basically in this solution is these three things: H plus, Cl minus, and sodium ions, right? So now when I go and add some HCl to it, I am adding more H plus and Cl minus, which means I just really increase the amount of H plus and Cl minus, which means this is why that combination will not work as a buffer, because as you can see in this picture, I now have a ton of H plus that was just formed, right? And I would see the pH go pretty big jump in this case. And that is why you cannot do it out of a strong acid or even a strong base. It has to be a weak acid and weak base, as those are the only two that can actually set up the equilibrium and keep both of those parts in the solution at the same time. Any questions on that there? So essentially, if you think about it here, you usually, when you make a buffer, for example, will try to keep the acid part and the base part of their buffer. So in our example, like the HF and the F minus part, kind of equal to each other in terms of their concentration. So when you add acid to this buffer, what's going to happen is it's going to react with the base part, but as we saw, you will make, in dramatic drawing purposes here, you will make more of the acid part, and you'll use up a little bit of the base part of the buffer. And if you add some base to your buffer, it will react with the acid part, and again, dramatic drawing here, you will have a lot more of the base part than you do the acid part in this case. And this is why buffers can sort of resist changes in pH over a good period of time, because you're kind of regenerating part of the buffer as you're using it. And as long as you don't go overboard, your buffer will be okay. There is what is known as buffer capacity, which means not all buffers are good. And when you make a buffer, there's two things that you want to think about. You want to think about the actual molarity of your buffer, and you want to think about what the molarity of your acid or base that you might be adding to it. You can make a buffer that actually is a buffer, but you could add way too strong of acid or base to it, and you'll blow right through the buffer. So for example, the buffer that you made, I forget what you were adding to it, 1 molar maybe or something, or 6 molar. So maybe you grab 18 molar off the shelf. You would blow right through that buffer. Your buffer couldn't handle it. It's too strong. So it's really important when you make buffers to understand what you're going to be adding to it in terms of their concentration of acid and bases and the actual molarity of the buffer itself, to make sure that the buffer has a good capacity to work really well in your situation. So let's just say, for example, we did that, not that anybody would do that, and you read the instructions wrong, and instead of 1 molar hydrochloric acid, you grabbed like the 18 molar hydrochloric acid, right? Or you just kept adding acid. What would happen in this case if I just kept adding acid to this buffer? Every time I would add acid, I'm going to chew up some of the base part, right? And as I keep adding it, I'm going to chew up more and more and more until eventually, if I either grab too strong of an acid or added way too much, I'm not going to have any more of the base part of the buffer left. At that point, if I continue to add acid, so if I continue to add acid after I kind of used up all the base part of the buffer, what's going to happen in a solution? I'm going to start adding now lots of H plus, right? Because there's no base in there to kind of neutralize it or use it up. And now what you will see is your pH will jump really far. So you actually, if you had a buffer, you would actually know how quickly or when it's over, because you would see a very big jump in pH. This actually happens, and you actually experience this when you did your titrations. If you remember, you did your titrations, and we talked about how the pH jumps a lot, right, as you get to the equivalence point. And when you added just the 1 drop, right, your buffer made your titration maybe went from colorless to like dark pink, right? And that's because you jump pH a lot. So as you're doing that acetic acid titration, for example, before you get to the equivalence point, you actually created a buffer. And when you add like that 1 drop, you have now just blown through the buffer part of it. And that's why you see that really big jump in pH to the equivalence point. And that's, as we talked about, because the indicator works on pH change. That's why you see a really big change in the color of it at that point. Is because you actually made a buffer as you were doing the titration, and then you blew through the buffer as you went past that point. Question on how buffers work. So essentially, because they have an acid part and a base part, when you add additional acid or base, it's able to prevent the formation of free H plus or free OH minus. Both of those are going to pretty much maintain your pH as to where it started. Any questions on any of that there? All right, that was, I think, should wrap it up. And there's, again, a table from your book, again, what it makes. And these are the generic reactions that occur. If you add acid, you will make the acid part of the buffer. If you add base, you'll make the base part of the buffer, as we see there. Okay, so this is chapter 17, which is equilibrium, the last one here. So equilibrium basically involves a certain type of reaction that occurs, and that is basically one that has 2 arrows. So equilibrium, as we'll talk about in this chapter, basically involves reactions that have these reversible arrows. And once again, these reversible arrows means that this reaction basically has 2 directions. It again has a forward direction, which is as the reactants go to products and start to make products. What will happen in these cases, in these reversible reactions, is at some point you will actually make enough products that they will decide we're going to go back the other way. So you, at the beginning, typically you don't have a lot of products. So at the beginning, it's going to be all the forward reaction kind of happening in most cases. At some point, you will make enough products that they will start heading back the other way. And that's what's considered basically the reverse reaction, when our products start to combine to make our reactants. And eventually this reaction will come to, as we'll talk more about in this chapter, what is known as chemical equilibrium. So we'll see it in a couple places here as we go through this chapter, but the one thing that it doesn't mean, which sometimes is confusing to a lot of people, is the name says equilibrium. So sometimes people have the idea that you have equal amounts on both sides of the arrow of everybody, and that is really not what it means. What it actually is referring to, as we'll talk about here as we go through this chapter, is it's actually the point where the rate of the forward reaction will equal the rate of the reverse reaction. So when something actually reaches chemical equilibrium, it doesn't necessarily mean that you have the exact same amount of everybody on each side of the arrow and everybody's equal, like you got 4 of everybody. What it means is just as fast as it goes from reactants to products, it will turn back around and go from products back to reactants. What that essentially does is it locks everybody into place where they're at that point. So whatever their concentration is at that point, or you can actually look at pressures as well, whatever their pressures or concentrations are at that point, they're going to pretty much maintain them, because just as fast as some of that reactants lose, it comes back the other way. So just as fast as it goes one way, it comes back the other way, which locks everybody into place exactly where they are when it reaches equilibrium. That again doesn't mean that they all have the same amount. So for example, this thing could get into equilibrium and maybe there's 4 molar of this guy, there's 2 molar of this guy, 1 molar of this guy, 3 molar of this guy. So what that would mean, for example, is if we reach equilibrium, that's pretty much going to be their concentrations until you do something to screw up the equilibrium. So if you don't do anything to screw up the equilibrium, they'll just keep maintaining those concentrations, because just as quick as it goes one way, it will break back the other way, and that will be locking pretty much everybody into place. Any questions on that there? So let's talk a little bit about how reactions occur. Again, the idea is a collision model. So molecules must collide in order for a reaction to take place. So there's really 2 things that has to happen for products to actually be made. And by the way, again, a reminder, in chemical reactions, all we are doing, right, are breaking bonds right on the reactant side and reassembling new bonds on the product side. So just electrons being sort of used here. So 2 things really has to happen for products, for example, to be formed. They do need to collide with each other, but they also have to collide with the proper amount of energy to allow that reaction to take place. And they actually have to hit each other kind of in the right area as well. So kind of like the active spot of the molecules, they kind of have to hit each other correctly and with the right energy to allow this reaction to take place. Now, the rate at which this occurs, and the rate is how fast or slow something occurs, does depend on the concentration and temperature. And as we'll talk about, obviously, if you have a greater concentration, there's a greater chance of everybody running into each other because there's more molecules moving around. And at a higher temperature, they probably also have much more energy to have the right amount of energy for this reaction to take place. So as we can see here, 2 BRNO molecules approach each other at high speeds. We get a collision that occurs. The energy of the collision causes the bonds to start to break, which is these dotted lines here. And it also allows the new bonds to sort of form between, say, the 2 BRs, which is right about there. And then our products occur. So this goes back also to, I think we might have talked about it in the energy chapter, the sort of activation energy, which again is that minimum amount of energy required for reactants to get up and over the hill to the other side to make our products. Not all collisions will result in products being formed. So again, if they hit each other in sort of the wrong location, or they hit each other with not the right amount of energy, you will not get products to form. So just because 2 things sort of collide with each other, those 2 things are really important for products to form. So things that can affect the rate of reactions, concentration, again, is a big part of it. So when you look at something like concentration, like molarity, which is moles per liter, it really is moles of solute per liter of solution. When you have a solution, it is pretty much the solute part, right? A solution is made up of two things, a solute and a solvent. It is the solute, the stuff that's dissolved in the solvent that's floating around in the solution, that really is what is going to react. So if you have a large concentration, that means in the case of molarity, you would have a high molarity, which means you have a lot of solute. So you have a lot of stuff floating around that solution. And because of the presence of all those things, that's going to allow molecules really just to find each other a lot quicker. They don't have to go swim around the entire beaker to find somebody, right? There's going to be somebody right next door bumping into them, and that will lead to probably more collisions and more reactions happening, and that will increase the rate. The opposite is true as well. If you had a much lower concentration, that means you would have less things floating around, right? Less solute molecules floating around. It's going to take a lot longer for them to find each other, and that's going to result in less collisions happening and also a lower rate as they're floating around. So it's kind of like the idea of in a room, and we'll just draw a beaker, right? So if my beaker is, if this is what's happening in the solution, there's a lot of solute molecules. There's a pretty good chance somebody's going to bump into each other pretty quickly, and you're not going to have to wait a really long time. As opposed to like if you were in just like an empty room with you and somebody else, right? It's going to take a little while for those guys to go find each other, right? So that's going to really slow down how fast the reaction is going to occur. Temperature as well. Again, temperature is a really big factor in terms of rates of reactions and how fast a reaction occurs. If you increase the temperature, a couple of things are happening. Besides more molecules having more energy, which means they probably could get up and over that hill. Again, a reminder, you know, when you have a reaction, those energy diagrams we looked at, right? Our reactants, our products, we have this activation energy, which is that hill the reactant's got to climb again to get to the other side. So with a higher temperature, we're going to have everybody that has a little bit more energy, which means you're going to have a greater proportion of molecules that will have enough energy to get up and over to the other side. In addition, if things are at a higher temperature, everybody's going to be moving around a lot faster, right? Which means they are going to come find each other a lot quicker than they would at a lower temperature. At a lower temperature, there would be less overall energy, which means there will be a smaller proportion of molecules that have enough energy to get up and over to the other side. Also, everybody will be moving around slower. So as they come in contact with each other, they're not going to come in contact with each other as much energy, which means you might not get the right amount of energy for that reaction to take place. And that's going to slow down the rate of the reaction. So those are two really big things that lead to either really a faster reaction or a slower reaction. If you were doing some type of rate reaction or experiment, you did it at room temperature, and then you took like your flask that you did the reaction in, and you let them sit in a hot water bath, you would see it would occur a lot quicker. And if you took those flasks and you threw them on ice and cooled everybody down, it would probably occur a lot slower. In general, if you increase the temperature about 10 degrees Celsius, for a lot of reactions, that's enough to double how fast it occurs. So a lot of times just increasing about 10 degrees Celsius for a lot of reactions is enough to really double how fast a reaction or the rate of the reaction will occur. Any questions on that there? So again, that activation energy, which is E of A, is that minimum amount of energy that's required for this reaction to occur. So that's what we're talking about when they collide. These reactants, as they are coming up the hill here in terms of energy, what you're starting to get after they collide is we're starting to break some bonds and we're starting to make some bonds. And if you remember up here, as we talked about, I think in the energy chapter, this is what is sometimes referred to as the transition state. And that is the transition state complex is sometimes referred to. That is that guy with partially broken bonds, partially made bonds, and doesn't hang around a really long time, right? Because it can drop back down very quickly here to our products. to make our products. Also a reminder, when we look at these energy diagrams, this where we have reactants higher in energy than our products, that is exothermic, right? We have to release energy to do that, right? Energy is being given off. And when we look at an energy diagram where it's sort of like this, reactants to products, where we have our activation energy, our reactants are lower in energy than our products. That's an endothermic process. Energy's got to be put in to do that. Remember, the difference between our reactants energy and our products energy was our delta H that we talked about, right? Our change in enthalpy, right? The difference between these two. And again, if you calculated that for each of those, one would be positive, right, for our endothermic, and one would be a negative value for our exothermic when you look at that. So again, that hill is also really your energy barrier to get to the product side. So I think, as we talked about in that chapter as well, and a reminder that the greater the hill, the probably slower the reaction is going to take, because you're going to have a less proportion of molecules that could get up and over to the other side, versus something that has a much smaller activation hill, which means there's probably going to be a greater proportion of molecules that do have enough energy to get to the other side. As we also talked about, and as we probably see here as well, one way that you can combat the activation energy hill is you could add something like a catalyst, right, which will lower the activation energy, and that also will speed up a reaction. So one way that we could kind of speed up this reaction is to add a catalyst. And a catalyst, a reminder, is not a reactant. And again, it's not a product, and it does not get used up. It is there essentially, again, to find an alternative pathway for this reaction to take place. Really a more efficient sort of pathway for this reaction to take place. The result of that is it essentially will lower the activation energy, or the hill that the reactants has to climb to get to the other side. The result of that is, because it's more efficient, less energy to get to the other side, you're going to have a greater proportion of molecules, reactant molecules, that can do that and have enough energy, which is going to result in an increase in the rate of the reaction, because you're going to have a lot more reactants be able to get to the other side, to the product side, without a lot of work sort of happening. In sort of biological systems, we use enzymes to do this. For example, we actually used a catalyst in one of our experiments, which was the potassium chlorate one, where you put it in test tube, heated it up, and made the oxygen gas. It was a mixture of potassium chlorate and something else. That something else was actually the catalyst they just threw in there to make that reaction sort of occur a lot quicker. We oftentimes will use catalysts. Catalysts, again, are oftentimes written on top of the arrow. They can be metals in certain cases. They could be like an acid, or a base could be used as a catalyst, which are sort of the conditions or the environment to help things sort of react a lot better. All right, any questions on rates of reactions here? So let's talk officially here about equilibrium. Once again, equilibrium is the balancing of two processes, the one which happens in opposites of each other. Places where we very commonly see equilibrium occur is actually where we change phases. So when we go from one phase to the next. So for example, if you remember, as we go from solid to liquid, or liquid back to solid, for the case of water, that occurs at 0 degrees Celsius. That's the normal melting point or freezing point. If you remember that heating cooling curve, which I think is in one of those chapters on the exam, so hopefully you remember it. I hope you know. That was the flat portion, right, of the graph. And that was say 0 degrees Celsius. And obviously that was say ice in the case of water and our liquid water happening here. So right at 100 degrees Celsius, we have this plateaued line, which means we're not changing the temperature or anything like that. But that's an equilibrium process because right at a 0 degrees Celsius, for example, in the case of water, you have ice crystals happening. So you have solid happening and you also have liquid sort of happening at the same time. It's not again till you get a little bit above or below that you really do transition from one phase to the next. It also happens as we see in these beakers here at say 100 degrees Celsius here. And that is between liquid and gas, right? These two phases as you go from liquid to gas, gas back to liquid. In the case of water, that's 100 degrees Celsius where that occurs, the normal boiling point. It also occurs at the surface of a solution. And I think we saw this in one of those chapters as well. If you have a solution and you put it into a capped glass, in this case, what you're going to first have is the rate of evaporation is going to increase a lot. And what's going to happen in this case, because you have a cap on it, it cannot completely escape the flask. It's stuck in there basically. So at some point, it's going to kind of come up here and decide, we're going to go back the other way. And eventually it will come to equilibrium. And I think as we talked about it, you'll see a little bit of a change in the overall volume of the solution because you have some vapor above the liquid at that point. But it will come to equilibrium. So changes of phases is very common equilibrium things that we see. The obviously experiments that we did there last week at the end were all equilibrium experiments, and they are reversible sort of things. So as we go here in this dynamic state, we get our guys to start to evaporate. We'll get our slower moving guys starting to drop down. Eventually, what we will have in this example here, the rate of evaporation will equal the rate of condensation in this case. So the rate of evaporation will equal the rate of condensation. Now, when we look at something that is at equilibrium and a solution that is at equilibrium, we sometimes look at it and go, well, it's over. Not much is happening, right? So, for example, when you added those whatever solutions to your test tubes in that experiment, not the best example, but you had like that dark red one. And it looks like, well, maybe it got lighter, it got darker, but it kind of just stayed at that point, right? It didn't look like it was moving much after it went one way or the other, right? It made that color. And it looks like, for example, that the reaction is over. And it's really not over. It may be over on the sort of macroscopic level where we look at it with our eyes and go, not much is happening. What turned yellow? Terrific. But there is a lot of activity that's happening to keep it at yellow, right? So when we have a reversible reaction, it may look static on the macroscopic level, but on the microscopic level, there's a lot of activity that's happening. We have the forward direction of that reaction happening. We have the reverse direction of that reaction happening. So although it just looks like, hey, your test tube turned yellow and it's over, there's a lot of activity. If you were to super zoom in, you would see reactants go into products, products go into reactants, a lot of activity happening. It's not like over, everybody's done, everybody's taking a vacation at this point. There's a tremendous amount of reactive activity happening to maintain that solution at that point. So it's unlike a sort of non-reversible reaction where pretty much, for example, everybody drops out to the product side and nobody on the product side is going back the other way. So it's just going to be kind of over, if you will, with these reversible reactions because they're happening at the same time, at the same rate. There's a lot of activity to make it when you look at your test tube with just your eyes go, it's over, it turned red, it's over, nothing much is happening at that point. So always activity happening in a reversible reaction, even though to our naked eye, it may not appear that there's much happening. There's a lot of activity sort of happening under the surface, I guess is a way to say that. So here's an example of a reaction of water and CO to form CO2 and H2. And once again, when it reaches equilibrium, what we are talking about is, again, that rate of the forward direction equaling the rate of the reverse direction. We're not talking about having equal amounts of everybody. So for example, here you can see as we start this reaction, we pretty much have all reactants, no products. So as we start going, we do have to decrease the amount of reactants to increase the amount of products. At some point, we'll have a good amount of products that these guys will start maybe going back the other way. And again, eventually it will reach equilibrium, and the rate of the forward reaction and the reverse reaction will equal each other. And that's what we see in this picture. At the very beginning here, we pretty much have only the forward direction happening because we have no products. As you can see down here, no products happening. Again, so at the very beginning, it is all reactants to products. Then what will happen at some point, we have some products being formed that will go back to reactants. And that's what we see here. We see an increase in our products. We see a decrease in our reactants. And at some point, what you will see is their concentrations stay constant. And that's usually represented in a drawing like that as a straight line, a plateau line. That means that their concentrations are not changing at this point. And that is the point where they have reached equilibrium. So that point where they first start, everybody levels out. That will be the point of equilibrium. Although in this graph, it may appear that both the reactants and the products will level out at the exact same concentration. That's not the case. You could have a graph where you see something like this and our products go something like that. And right about there would be where it reach equilibrium, where they both flatlined out. So although it may appear here that they will flatline out at the same concentration, it's not always the case. They can just flatline out wherever they're at, and that is where they will reach equilibrium. Any questions on that there? So chemical equilibrium, again, is the point where it is, again, the rate of those forward reactions and reverse reactions equal each other. Again, not necessarily the same amount of each. So let's take a look at this one and talk about what might be happening here. Let's say we had an equilibrium mixture in a closed vessel. And at that point, it sets up this equilibrium of the water and the CO, or CO2 and our H2 in this case. So what that means is in this container, we'll close it. We pretty much have everybody there. Yeah, we got everybody in this container. And again, that is pretty much the same idea. It's a reversible reaction. It's kind of like a weak electrolyte. It's going to all be in there together. And if I decided to add more water or steam to this container, how would all of the concentrations change in this case? So if I added some H2O in this case, which is over here, so if I added more of this guy, let's start with this one here. What would happen to the amount of CO in this case? Would it be more? Would it be less? Would it stay the same? Should it go up, down, stay the same? What do you think? So 33 1/3 shot there. It should actually go down. So in this case, we should actually see the concentration of CO go down. Why does it go down? Because when I add more water in this case, or steam, however you want to word it, when I do add more water or steam, that's going to cause more reactants to be present, and that's going to cause the actual forward direction of this reaction to take place. As we just talked about, right, rates of reactions are dependent on concentration. So what you essentially just did is you increase the amount of reactants, which means they're not going to have a very hard time finding each other, right? So they're going to be able to find each other a lot quicker. And that is going to cause the forward direction basically to occur, which means I should see a decrease in CO because I need it to make my products. What should happen to my H2 concentration? Should it go up, down, or stay the same? It should increase, right? Because we're making products. And my CO2 concentration should also increase, right? Because we're now doing the forward direction. We're making more products. How about my H2O that I added? What's going to happen to that? It is going to actually go up because you added it, right, artificially. But then it should start to go back down as it reacts with the CO, right? So you may actually end up more than you started with, and that's only because you added it. So you kind of artificially inflated it. But as it gets inflated, it will start to react with the CO in this case and start to come back down. So when we do this, in this case, we're essentially, again, adding more reactants, which is going to increase the availability of those reactants to react with each other. They're not going to have to go find each other. And that's going to cause the forward direction of this reaction to really take over. And that's going to lead to more products being formed in this case. And that is why, for example, when you added some products to your equilibrium reactions, you saw, when you added more reactants to your equilibrium reactions, you saw products color being formed because you just kicked off the forward reaction to occur when you did that. Any questions on that? All right, so let's say we had, let's see here. Let's say we had the same equilibrium here and we add some H2 in this case. So we're going to add some H2, which is over here. We'll start with the amount of H2O. Will it go up or will it go down? Will it stay the same? Yeah, in this case, when we add more H2, we now have made actually more products available to each other. So these two guys are going to be able to react a lot quicker, and that's going to cause the reverse reaction basically to occur. And because of that, we then should actually, in this case, make more reactants. So we should see the H2O concentration go up. We should also see the CO concentration go up. The CO2 concentration then should also go down in this case, right? Because we need it to make the reverse reaction occur. And in the case of the H2, we will see a very similar type of effect. We will see the H2 go up and then come back down as it's reacting to do the product reaction. Any questions on that? So that's also why when you added a product to one of those reactions that you did in Le Chatelier's principle, you basically force the reverse reaction to occur because you have a lot more products than reactants in that case, and that would shift it to the reactant side color. Any questions on that? Yeah. Yeah, so basically when you do this, you can think of it like we have a lot more products at this point, and that's going to cause that reverse reaction to occur, which is basically the two products coming together to make the reactants. So because of that, every time you have the H2 reacting, you got to have some CO2 reacting with it, which is going to bring ultimately both of them down. But the H2 might end up higher than it started with only because you added it. Other than that, its main direction will come back down as well. Other questions on that? All right, let's see here. So let's take a little look at the equilibrium constant. The equilibrium constant is the letter K, and it is capital K as smaller case K as your learn. 1B, I think, where they teach it here, is the rate constant, which has to do with the rate in kinetics, but capital K, which is essentially what 1B class is brought to you by the letter K, is the equilibrium constant. And to write the equilibrium constant, when we have a reaction such as this, we take our products, basically, divided by the concentration of our reactants. So once again, the little bracket is concentration, and that usually is molarity, moles per liter. And we do take the coefficient as the exponent. So we would take the concentration of C to the C power, whatever it may be, the coefficient, the D coefficient to the D there, and our coefficients there. So from the balanced equation, the coefficients become the exponents, and we take the products over the reactant concentration. When we do it with concentration, this is sometimes referred to as the Kc value. C meaning concentration. There's Kp, which is the pressure, because you could actually do this if these were all gases. You could write what is referred to as a Kp if they were gases. And it would work the same way as the partial pressure of C to the C, partial pressure of D to the D, divided by the partial pressure of A to the A, B to the B in this case. So if you happen to have a equilibrium that were all gases, a lot of times you would be looking more at pressures rather than concentrations. You can write what is known as a Kp value. We've already seen an equilibrium constant. That is our Kw. Yeah, that is an equilibrium constant for water. So it's the same idea. You also, if you take 1B, learn about Ka, Kb, Kf, Ksp. There's a lot of Ks. The whole entire class is all about it, basically. So they're all, though, really equilibrium constants. The nice thing about equilibrium constants is two things, I guess, or one thing. In order to calculate it, you do need equilibrium concentrations. So they has to be the equilibrium concentrations to go into here. Or if we were doing pressures, it has to be the equilibrium pressures of each of those guys. When the system comes to equilibrium, so that's the point where the rate of the forward reaction and reverse reaction equal each other, there has to be those concentrations. After all the yelling about units, is the nice thing about this is just a number. So the value of K is actually just a number. There's no units associated with it. So to finish up here, what does this number tell us? If we have a large value for K, if I have a large value for K, what that means is when I reach equilibrium, should I mainly have reactants or products there if I have a large value? I would have mainly products, right? Because I'm basically dividing products divided by reactants. So the only way to get a large number is this number needs to be big, right? So I would have mainly products present when I reach equilibrium. And if I have a small value of K, that means that I mainly have reactants present when I reach equilibrium. In order to get a small value of K, you need the bottom guy there to be larger than the top guy, and that will give you that small value of K. What is considered a large value or a small value? It is the really big number of 1. Yeah, 1's considered large. So anything above 1 is considered a large value of K. Anything less than 1 is considered a small value. There is basically big degrees of difference in that. You could have a K that is like times 10 to the 32, and you could have a K value that's like times 10 to the minus 56. So very small values, very large values. But that's essentially what the K value will tell you. Any questions on that there?